Exercise 6.3 is asking you to predict whether entropy, delta S, increases or decreases in a few reactions. So, first, what is entropy? What is delta S? Delta S is really just probability. It's the probability it's the probability of having molecules arranged in a certain way. The more ways there are to arrange molecules, the more likely you'll have that arrangement, and so the more likely that that arrangement will exist. And when you have a higher arrangement or when you have molecules that can be arranged in more ways, another way of saying that is you have high entropy. So there are two patterns for entropy that you want to remember. The first one is that if you go from few molecules to lots of molecules, or let me say few to more, in that case, entropy increases. If all the atoms you have are stuck in just a few molecules, then you can move those molecules around, but there are only so many. But you're limited you're limited in the arrangement of those atoms by the fact that the atoms have to be stuck together. If, on the other hand, you have those same atoms, but they're separated from each other, you can move them around in lots more ways than if they're all together in one molecule. So the more you break molecules apart to get more molecules, the more likely that arrangement is going to be, because there are more ways it can exist, and so the entropy is bigger on this right side. So you're going from less entropy to more entropy, and you would say that entropy increases. So there are fewer ways for that to be arranged, so that has less entropy. If you turn them into more molecules, you can arrange them in more different ways, so it's more likely that that will exist, so that has more entropy. So if you go from less entropy to more entropy, the entropy increases. And symbolically, you can say that as delta S, which is the entropy, is positive. It increases. When the entropy changes, it gets bigger. Okay, so I'm going to erase the words here to make this a little cleaner. What you want to remember is that if you go as you cross the reaction arrow, if you go from fewer molecules to more molecules, then entropy increases. And if you went the other way around, if you went from more molecules to fewer molecules, then the entropy would decrease and delta S would be negative. So this way is positive, the reverse way would be negative. So that's one thing. The other thing you have to watch out for is whether you have a straight chain or a ring. Now a ring has its bonds can only rotate in a limited number of ways. That limits the number of ways that that molecule can exist. And so there are fewer ways it can exist, so it's described as having less entropy. It's less likely to exist. If you go from a ring to a straight chain, in a straight chain, all of the bonds can rotate if they're single bonds. And so because all the bonds can rotate, there are many more ways that those bonds can exist. And so they're more likely to exist, and so you can describe them as having more entropy. So again, if you go from less entropy to more entropy, then entropy increases. The likelihood of the arrangement of molecules increases. And you would describe that symbolically as delta S is positive. The entropy change is getting bigger. The molecules are more likely to be arranged in that way. So that's when you go from a ring to a straight chain. So you have these two ways for just qualitatively looking at a reaction and telling whether the entropy increases, whether the products are more likely to exist or not. The products will be more likely to exist if you broke the molecules apart, so you made more molecules. The products will also be more likely to exist if you turned a ring into a straight chain, because there's more ways that the straight chain can exist. And if you have the reverse of these, if you have fewer molecules in your products, or if you make a straight chain, you force that into a ring, the entropy decreases. Delta S would be negative, and that reaction would be less likely to happen all by itself. So those are our two rules of thumb for trying to figure out whether delta S is positive or negative. And this will be useful because we can use this information to change equilibrium using the temperature, as we'll discuss in a future video. So we can use this information to adjust the equilibrium, make the equilibrium favor products more or reactants more, depending on whether we want a reaction to happen or not. So in this first one, in A, we'll go through each of these factors. First, how many molecules do we have on the left? We have 1, 2. So 2 molecules. How many molecules do we have on the right? Just 1. So we're going from more molecules to fewer molecules. That's like going the reverse of this, and the entropy is decreasing. So delta S here would be negative. There are many, many ways that these two molecules can exist. There are fewer ways that they can exist if they're all stuck together, and so it's less likely that they'll be stuck together, just because there are fewer ways that that can happen. So the entropy is decreasing. That's by the first consideration, and if you look at the second consideration, that also suggests that the entropy is decreasing. You always have to look at both considerations. So here we start with a straight chain. We start with straight chains. It's easier for those to rotate. The double bonds can't rotate, but it's easier for them to rotate here than for the ring to rotate. So you start with straight chains, and you end up with a ring. So that's like the reverse of this. And so that also suggests that the delta S would be negative, because there are many ways that these straight chains can exist. There are fewer ways that the ring can exist, and so the probability of the molecular arrangement is going from more likely to less likely. Delta S is negative. So when you look at both considerations, the number of molecules and the straight chain versus the ring, the entropy for A is definitely decreasing. Delta S is negative. All right, for B. Well, if we look at the first consideration, the number of molecules, we have 1 molecule on the left and we have 1 molecule on the right. So that's a wash. But if you look at the second consideration, you have a straight chain on the left and you have a ring on the right. You're going from a straight chain to a ring. That means that the entropy is decreasing. Delta S is negative. There are many ways the straight chain can exist when the single bonds rotate. There are fewer ways that those bonds can rotate when they're all stuck in a ring. And so the entropy is decreasing. You're going from something that's more likely to something that's less likely to exist. So the likelihood of the reaction is decreasing. The entropy is negative. Okay. If then we go to the C and use the same sort of thinking, so the first factor, let's look at the number of molecules. On the left we have 1 molecule. On the right we have 1, 2 molecules. So we're going from fewer molecules to more molecules. The entropy is increasing. So that would suggest that delta S is positive. This molecule, with all those 6 atoms stuck together, can only exist in so many ways. If the atoms can move apart as separate molecules, there are more ways that they can exist. They can still exist close together, but then they can also exist far apart, so there are more ways they can exist, and so they're more likely to exist in this way. So the likelihood of the molecular arrangement is getting bigger as you go from the left to the right. In other words, the change in entropy is that the entropy is increasing. It's positive. So that's looking at that first factor. And if we look at the second factor, we'll see that it corroborates it. Notice we start with a ring, and we end with straight chains. So because it's in a ring, the bonds can't rotate, all the bonds can't in fact, none of the bonds can rotate 360 degrees. In a straight chain, it's easier for the single bonds to do that, and so the molecules can exist in more ways, so it's more likely that they'll exist, because there are more ways that it can happen that they exist. And so, as you go from the left to the right, you're entering a more likely arrangement for the molecules, and the entropy, the likelihood of the molecular arrangement, is increasing. So both of the factors there indicate that the entropy is positive there. Delta S is positive, the entropy is increasing. If we look at C, first factor, we have one molecule on the left, we have two molecules on the right, so we're going from few to more molecules. That would suggest that delta S is positive. When the molecules are all stuck together, there's a smaller number of ways for them to exist. When they're apart, they could still exist in all the ways where they're close, but now they can also exist in more ways where they're apart. And so there are more ways they can exist. So if you go from lesser probability to higher probability, the change is that the probability of the arrangement of the molecules is getting bigger. And so delta S for D there is positive. That's with the first factor. And if you look at the second factor, it doesn't change. We don't have any rings in either the reactants or the products, so that doesn't shed any light on our analysis. But because of the number of molecules, we could tell that in D, delta S is positive. The entropy is increasing. For E, we start with two molecules. Now I know it's a little weird here. They're writing one of the reagents on top of the arrows. That's a difference between organic chemistry and general chemistry. In general chemistry, they always write the reagents to the left of the arrow, but sometimes in organic chemistry, they'll write one of the reagents on top of the arrow, because they want you to focus on the carbon molecule. So it's just another way of adding emphasis. This is like raising your voice a little or putting it in italics. You want to look at that carbon molecule. And this is indeed another reactant, but it's not the one you're most interested in necessarily. And so you're putting it on top of the arrow. So in this case, we have two reagents, one that's to the left of the arrow, one that's on top of the arrow, so we have two. And then on the right, we only have one molecule. So we're going from more molecules to fewer molecules. That's the reverse of this first factor. And so the entropy seems to be decreasing. Delta S seems to be negative. When these molecules are separate from each other, they can exist in a lot of ways. Some of them are having them close to each other, some of them is having them further from each other. But once they react and they form a bond, they can only exist in the ways that are close to each other. And so there are fewer ways that that molecule can exist, and so it's less likely to exist than these reagents are. And so if you go from the more likely way to the less likely way, the probability changes, it decreases for the arrangement of the molecules. In other words, delta S is negative. And if you look at the second factor, the ring here, we don't have any rings on either side, so that doesn't influence our analysis. Finally, for F, in F, if you look at the number of molecules, on the left we have 1, on the right we have 1. So that's a wash. The number of molecules doesn't help us here, but if we look at the second factor, we see that we have a ring on the left, and we have a straight chain on the right. We have a straight chain on the right. And so in this reaction, you go from something that's less likely to happen to in the ring. None of the single bonds can rotate 360 degrees. You'd have to break the ring in order for them to do that. So there are fewer ways the ring can exist. In the straight chain, all of the single bonds can rotate 360 degrees. There are a lot more ways that that molecule can exist, and so it's more likely to exist. So if you're thinking about how the entropy, the likelihood of the molecular arrangement changes, well, it gets bigger when you go from the ring to the straight chain. and so delta S is positive. And so just to give you a sense, so that's how you can assess the entropy for each of these reactions. You look at those two factors, and just to give you a sense for how you can use this in a laboratory. So this is a nice conceptual thing, but if you go into a laboratory, what difference does this make? How can you make this useful? Remember that the likelihood of a reaction happening is delta G. If it's likely to happen, it'll be negative. If it's unlikely to happen, delta G will be positive. And delta G is related to the heat, the change in heat, minus T times the change in entropy. Well, in these examples, we figured out the sign of entropy. Notice whatever the sign of entropy is, it'll contribute the opposite sign to delta G because of the negative sign in the equation. So if delta S is positive, then because you subtract it, it'll make delta G more negative. If delta S is negative, because you subtract it, subtract a minus sign, it would make delta G more positive. And that should make sense, because if delta S is positive, then the molecular arrangement is more likely, and you would think that would make the reaction more likely to happen. And if delta S is negative, then the molecular arrangement is not very likely, and you would think that would make the reaction less likely to happen. But notice that the influence of delta S here completely depends on the temperature. So if delta S is unfavorable, if the entropy decreases, but we still want the reaction to happen, we can minimize the effect of delta S by lowering the temperature. If you lower the temperature of this reaction, it makes the reaction happen faster, because the unfavorable molecular arrangement is now no longer as influential. It's just the arrangement of the heat or energy that matters. So again, if this reaction is not favorable, it's more likely the molecule will exist as the molecule on the left than the right. But we can decrease the effect of that by bringing the temperature down. The colder that reaction is, the faster it'll happen. In this example, the entropy is favorable. And so we want the entropy to be really significant in the reaction. All we have to do, raise the temperature. The temperature is multiplied by the entropy in this equation. If you raise the temperature, then entropy will steal the day. It'll determine the sign of delta G. And so if you want this reaction to happen faster, heat the molecule up, heat the reaction up. So in general, if delta S is positive, you can make that reaction happen faster at high temperature. High temperature would favor that. And if delta S is negative, you can make that reaction happen faster by making it colder, putting it at low temperature, putting it in an ice bath. Because temperature determines the influence of delta S in the likelihood of a reaction happening. But this exercise was just to show you how you can assess qualitatively, looking at a reaction, whether the entropy is increasing or decreasing using the change in the number of molecules and the